Hello everyone, welcome back to this online class. Today we are going to look at the method of Laplace transform as used in solving ordinary differential equations. Now we are given this question. We are asked to solve the following initial value problems. In part A, we have d squared y dt squared minus 3 dy dt plus 2y is equals to exponential negative t cos t. And the conditions are that y is equals to 1 when x is equals to 0, and y prime is equals to 2 when x is equals to 0. Part B, we have d squared y over dt squared plus 2 dy over dt plus y is equals to 3t times exponential negative t. The initial conditions are that y is equals to 4 when x is equals to 0, and y prime is equals to 2 when x is equals to 0. So, how do we solve these two problems using the method of Laplace transform? I want us to take note of what you mean by the Laplace transform. Of course, we are going to be using the L to be the Laplace transform operator. When it operates on a function f of t, it is defined by the integral from 0 to infinity exponential negative st times f of t dt. This is an improper integral, and the s here is a dummy variable. S is a dummy variable. Let me use another color. S denotes a dummy variable. And remember, s must be greater than 0. So it is a dummy variable that is chosen so that the improper integral converges. So this is the definition of the Laplace transform. And this method of Laplace transform is always used in solving initial value problems. You have an ODE together with the initial conditions. That's what we mean by an initial value problem, which is denoted by IVP. So having discussed such basic concepts, let's now look at part A. There are very few steps involved in solving such kind of a problem. The first step is to operate with L on both sides of the ODE. That should be step 1. So I can write here step 1. Operate with L on both sides of the given ODE. So we are going to write this, that the Laplace transform, let me call it y double prime, a function of t minus 3 times the Laplace transform of y prime as a function of t. Then the other term is 2y. Remember, y is a function of t, so plus 2 times the Laplace transform of y as a function of t is equals to the Laplace transform of the right-hand side, that is exponential negative t times cosine of t. So now we know how to find the transform of derivatives and also the transform of the function on the right-hand side. If you cannot remember, then you need to use the Laplace transform table. So the second derivative will give us this one, s squared times the Laplace transform of y, remember y is a function of t, then minus s times y when t is 0 minus y subscript t. That's derivative of y with respect to t when t is 0. Then we have minus 3. This other transform of the first derivative should give us s times the Laplace transform of y then minus y when time t is 0, plus 2 times the Laplace transform of y, remember y is a function of t, is equals to, now I want us to take note, let me write it here, because I can use red, that Laplace transform of exponential at times cosine of bt is equals to s minus a over s minus a, and this is squared, plus b squared. That is from the Laplace transform table. So in this case, if you look at the function on the right hand side, it is clear that our a is -1 and our b is 1. So if I substitute those two, I am going to get s plus 1. I'm replacing a by -1 and b by 1. So this will be over s plus 1 squared, then plus b squared, which is 1 squared, that is simply 1. So that's the first step. The second step, you need to apply the initial conditions. So y sub t here means y prime. That's what I mean. So I can just use the prime instead of subscript t. The prime means derivative with respect to t, still the same. Don't confuse them. The next step is, let me write here step 2. In this step, you apply the initial conditions. Look at our initial conditions in part A. We are solving part A. So our initial conditions are this one, that y0 is 1 and y prime 0 is 2. So I'll apply them here. Where we have y0, that will be 1. So this is 1. Y prime 0, that should be 2. Again here it should be 1. So let me write here that y0 is 1 and y prime 0 is equals to 2. So when we substitute those ones, what are we going to get? We're going to get s squared Laplace transform of y. Remember, I said y is a function of t, it's better to write y of t. Then minus s minus 2. Then we have minus 3s Laplace transform of y of t. Y is a function of t. Plus now we'll have -3 times -1, that should be plus 3. Then plus 2 times the Laplace transform of y of t. This should give us s plus 1 over s plus 1 squared plus 1. Then the next thing, you collect like terms. So we can just say collect like terms. You remember the like terms are this one, the ones with the Laplace transform. Let me group them together. So we'll have s squared minus 3s plus 2 times the Laplace transform of y of t. What do we remain with? We have -s minus 2 plus 3. That should be -s plus 1. So I can even take it to the right hand side, or let me write -s plus 1 is equals to s plus 1 over s plus 1 squared, then plus 1. Let me simplify this further. So I'm going to take the all of this to the right hand side, take it to the right hand side, so that we have, or s squared minus 3s plus 2 times the Laplace transform of y as a function of t is equals to s plus 1 over s plus 1 squared plus 1. So I'll have plus s minus 1. That's what I have. And then the next thing, you make the Laplace transform the subject. So you can say, or Laplace transform of y of t as a subject, it will be s plus 1 over s plus 1 squared plus 1, then plus s minus 1. Remember the whole of this, we are multiplying by 1 over s squared plus minus 3s plus 2. It's like dividing by s squared minus 3s plus 2. So the question is, now that we know the Laplace transform, how do we find the function y of t? That is the question that you need to ask yourself. And so the next step, call it step 3. In this step now, you operate with L inverse on both sides. Operate with L inverse on both sides of this equation, so that, remember, I want us to take note. Take note that when you have L inverse operating on L of any function y of t, the result will be y of t. Because L inverse and L are inverse operators of each other. They are inverses of each other. So when you operate, L inverse and L will give you identity operator. And identity operator operating on a function gives you the same function. So that what we'll have on the left-hand side is y of t should be equal to L inverse of s plus 1 over s squared plus, that's a minus 3s plus 2 times s plus 1 squared plus 1. Then I can see this plus s minus 1 over s squared minus 3s plus 2. So we need to get the inverse of that function on the right hand side. This is the question, how do we find the inverse? That's what you need to ask yourself, how to find the inverse of that function. So what you're going to do here, look at this function, s squared minus 3s plus 2. Are we able to factorize this? Yes. This can be written as, this is the same as, you're going to write the sum is what? The sum is negative 3 and the product is 2. So which two numbers will give you the sum to be negative 3 and the product is 2? So the numbers are negative 1 and negative 2. So that's s squared minus 2s minus s plus 2, which will give you s into s minus 2 minus s minus 2. So this is the same as s minus 1 times s minus 2. So that's what we have. What about the other one? The other one is s plus 1 squared, then added to 1. What will it give us? This is the same as s squared plus 2s plus 1 plus another 1, which is the same as s squared plus 2s plus 2. Are you able to factorize? Check. Can we find numbers whose sum is equals to 2 and product is also equals to 2? The sum is 2, the product is 2. You see, when you multiply 2 and 1, that's when you can get 2. So it means this one we cannot factorize. So let me just rub what I've written here so that this is a quadratic factor. Quadratic factor. So I can as well write this as L inverse of S plus 1 over, here we have found S minus 1, S minus 2 times S squared plus 2S plus 2. That's what we have in the first term. Then the other term is S minus 1 over S minus 1 times S minus 2. And you see I can simplify this. This will cancel with this. So I only have 1 over S minus 2. Now, what about this first fraction? Look at the denominator. It consists of products of linear factors and quadratic factor. There are 2 linear factors and a quadratic factor. So that we can use partial fraction to decompose this. So we are going to say let me write it here so that I create some space. I'm using partial fractions. So let S plus 1 over S minus 1, S minus 2, S squared plus 2S plus 2 be equal to A over S minus 1 plus B over S minus 2 plus CS plus D over S squared plus 2S plus 2. So when I multiply through by the LCM, I'm going to get this, or you multiply through by the LCM so that you get A into S minus 2 times S squared plus 2S plus 2, then plus B into S minus 1 times S squared plus 2S plus 2, then I can see plus CS plus D times S minus 1, take this to the left, times another S minus 2 should be able to give us S plus 1. So that this equation is true for any value of S that you choose. So if I say put S is equals to 1, if I say 1, you see this term, the term in B will disappear, and even the term containing C and D will disappear because there will be some 0 somewhere that you are multiplying with. So we'll simply have this one, A into 1 minus 2 times 1 squared plus 2 times 1 is 2 plus another 2. The others will be 0. 0 plus another 0 will be equal to 1 plus 1. So this is the same as, of course, is negative 5a. This simply means that negative 5a is equals to 2, of which you can say that a is equals to negative 2 over 5. So we have found a. Let me bracket this. We still need to find B and C and even D. So I can also make another substitution. Put S is equals to 2. What are we going to get? Let's see. The term in A will cancel because this S minus 2. So 2 minus 2 is 0. When you multiply by 0, you get 0. So the term containing A will disappear. And even the term containing C and D will disappear. So we only have the term containing B. So we'll have B into 2 minus 1, 2 squared, that is 4. So let me just write 4. 2 squared is 4, plus 2 times 2, that's another 4, plus 2 is equals to 2 plus 1. So what you can say here, this simply means that this 8, 10, that's 10b is equals to 3, or b is equals to 3 over 10. We have found b, we still need to find the value of c and d. So we proceed. Now, I also need to substitute any value. I can use even 0. So you can say put s is equals to 0. When I use 0, I'm going to get this one. Let me write it. I'm going to get a times negative 2 times 2 plus b times negative 1 times 2. Of course, c will disappear because s is 0, so I'll just have plus d times negative 1 times negative 2 is equals to 1. 0 plus 1, that's 1. But remember, we know the value of a. A is negative 2 over 5. And this one is negative 4. When you multiply negative 2 and 2, that's negative 4. What about b? We got 3 over 10 times negative 2. Here we'll have plus 2d is equals to 1. Or if I make d the subject, 2d is equals to, let's press that in the calculator. So we'll have 8 over 5, 8 over 5. Then the other one is negative 6 over 10, which is simply negative 3 over 5. So minus 3 over 5. Remember, it is this 8 over 5, then here minus 3 over 5. The answer is 1. And when you take it to the right-hand side, you get 0, 1 minus 1. So it's 1 minus 1, which will give us 0. So that means our d is equals to 0. That's very important. Lastly, we need to get c. I've used 1, 2, 0. Let me use negative 1 where there is s. So put s is negative 1. So what are we going to get? Let's see. It will be a times negative 1 minus 2, that's negative 3. Then here, negative 1 squared is 1. Then 2 times negative 1, that's negative. So we have 1 minus 2 plus 2. That should give us 1. That's here. Now let's come here. Plus b. Then negative 1 minus 1 is negative 2. This other one is 1 minus 2 plus 2. That's another 1. I'm through. Then here, I'll have plus negative c plus d. Then the other one is negative 2 times negative 3. Should give us negative 1 plus 1, that is 0. So remember, we know the value of a, the value of b, and the value of d. So we substitute. So you say or simply this implies that our a was negative 2 over 5. This one should multiply negative 3. Plus our b, which we got positive 3 over 10, should multiply negative 2. Our d is 0, so what we have here is 6 times negative c, so negative 6c. Remember, d is 0, so this should give us 0. Make c the subject. So I can say negative 6c is equals to, or simply you could take c to the right so that we have positive 6. So let me just rub this negative. Now what is it equal to? Here we have 6/5, so I'll press that, 6/5, then minus 6/10, or simply minus 3/5. That is 3/5. So I'll write here 3/5, so that you can now make C the subject. C, divide that by 6, so that you get 1/10. 1/10. Remember, it is 3/5 divided by 6. That should give us 1/10. So now we have the values of A, B, C, and D. So therefore, we need to go back to our fraction and replace whatever values that we have found. So let's go back and substitute the values of A, B, C, and D into what we have found, so that we are now going to write L inverse of, it is A over S minus 1. Our A is negative 2/5 over S minus 1. Our B is 3/10 over S minus 2. Our C, we have found 1/10, so plus 1/10S over S minus 1 times S minus, of course it is S squared plus 2S plus 2. Then the other one, after cancelling, we got 1/S minus 2. See, I have S minus 2 appearing twice in the denominator, so we can combine those so that we have L inverse of, let me write this as negative 2/5 into 1/S minus 1 plus 3/10 into 1/S minus 2. But you see, I can combine with the other one. So plus 3/10 plus 1, we can work out that 3/10 we are adding to 1. So that will give us 13/10. So let me rewrite this. I'll rub this so that I have there 13/10 into S minus 2, 1/S minus 2, then plus 1/10 S over, this one was the same as S plus 1 squared, then plus 1. So, how do we find the inverse transform? Look at the third term. I want us to take note. I'll write it here. Take note that S over S plus 1 squared plus 1 is the same as S. If I add 1, I need to subtract 1 over the same denominator, S plus 1 squared plus 1, which you can as well write as S plus 1 over S plus 1 squared plus 1, then minus 1 over S plus 1 squared plus 1. So that we can split this third fraction into two parts. So we can say hence, our y as a function of t is L inverse. Of course, you could factor out the constant. So let me just write, I'll factor out later. L inverse of negative 2/5 times 1/S minus 1 plus 13/10 times 1/S minus 2 plus 1 over 10 into s plus 1 over s plus 1 squared plus 1 minus 1 over s plus 1 squared plus 1. So that's what we have. And so we can distribute the inverse operator so that we have negative 2 over 5 L inverse of 1 over s minus 1 plus 13 over 10 L inverse of 1 over s minus 2 plus 1 over 10. Here we have this bracket, L inverse of s plus 1 over s plus 1 squared plus 1, then minus L inverse of 1 over s plus 1 squared plus 1. So that's what we have. There's another closing bracket. So now when you read from the table of Laplace transform, this is what you're going to get. So it will be equal to negative 2 over 5. I want us to take note that the Laplace transform of exponential at will give you 1 over s minus a. So now we are reading backward. So now we have 1 over s minus 1. In this case, our a is 1. So we'll now talk of exponential 1t, which is simply exponential t. Here we have plus 13 over 10. Here we have 1 over s minus 2. Our a is 2, so we now talk of exponential 2t. The other one is 1 over 10. Also, you know that the inverse of the cosine. So let me write it here. The Laplace transform of cosine bt from the Laplace transform table should give you s over s squared plus b squared. And so when you multiply by exponential at, already we wrote it up here. When that is multiplied by exponential at, this is what you're supposed to get. I don't need to write it again because already we have it written here. This one. Cos bt times exponential at will give you s minus a squared, then plus b squared. So that's what I'm going to borrow, so that I need to know what is my a and what is my b when getting the inverse. So in this case, our a is negative 1 and our b is 1. So we now talk of plus 1 over 10 into, here it is now exponential. Remember our a is negative 1, so that's negative t cos bt. Our b is 1, so that's just 1 times t. That's cos t. What about, you also know that Laplace transform of sine bt is the same as b over s squared plus b squared. So when it is multiplied by an exponential function, we'll now have Laplace transform of at times sine bt. What should it give us? It should give us b over s minus a squared plus b squared. So relate it with this one, so that in this case our a is negative 1 and our b is 1. So we'll have minus, that should now give us exponential negative t, because our a is negative 1. Then here we'll have sine t. So that is the solution for the ODE in part A. So you can just say, or y of t is equals to that. You see that the way this method is very easy. And remember, this method is only applicable when solving initial value problems. Let's work out part B. Of course, I'm not going to write so many things. Let me rewrite the equation in terms of the prime notation. The ODE in part B is, this can be written as y double prime plus 2y prime plus y is equals to 3t exponential negative t. So that's what I'll write here, our ODE. Y double prime plus 2y prime plus y is equals to 3t exponential negative t. And remember the conditions are that y of 0 is equals to 4 and y prime of 0 is equals to 2. So as usual, you take the Laplace transform on both sides of the ODE, y double prime plus 2 Laplace transform of y prime plus Laplace transform of y is equals to the Laplace transform of 3, of course 3 is a constant, I can factor that out. So is equals to 3 times the Laplace transform of t exponential negative t. You see, the constants are being factored out. Why? Because Laplace transform operator is a linear operator. So we talk of the linearity property of the Laplace transform operator. So when you operate on those functions on the left-hand side, you're going to get this. We'll have s squared times Laplace transform of y of t minus s y when t is 0 minus y prime when t is 0. Remember, that's the first term. Should give us that. Then there's plus 2. Again, transform the other one, you get s Laplace transform of y of t minus y when t is 0. Is this one here. Will give us this bracket. Then I can see there's Laplace transform of y on the right hand side. We have 3. Now, what is the Laplace transform of exponential negative t times t? I want us to take note that Laplace transform of t raised to n is the same as n factorial over s raised to n plus 1. When you transform a polynomial, that's what you need to get in general. And so when you use the first shifting property, if now the polynomial is multiplied by an exponential function, let's talk of t raised to n, what are you supposed to get? Remember, we are going to be using the first shifting property of Laplace transform. This will give you n factorial over s minus a raised to n plus 1. So that on the right hand side, our a is negative 1 and our n is 1. Look at t raised to 1 and exponential negative t. So put a is negative 1 and put n is 1. So this will give us 1 factorial, which is simply 1 over s minus a. So a is negative 1, so that would be s plus 1 raised to 2. S plus 1 raised to n plus 1. Our n is 1, so n plus 1 is 2. That's fine. Now let's apply the initial conditions. What is y of 0? That is 4. So this will cancel to 4. y prime of 0 will cancel to 2. Similarly, here we'll have 4. So that upon applying those initial conditions, we are now going to get s squared Laplace transform of y of t minus 4s minus 2. Then I can see minus, not minus, that's a plus 2s Laplace transform of y of t. Remember, I'm opening the bracket. Then minus, of course, here we have 2 times -4. That should be -8 plus the Laplace transform of y of t should give us 3 over s plus 1 squared. Let us collect like terms. So here, this and also this, we are going to combine them so that we have, or we talk of s squared plus 2s plus 1. This should be multiplying the Laplace transform of y of t. Then we have minus 4s minus 10 is equals to 3 over s plus 1 squared. And this could be written further as, you can write, or s squared plus 2s plus 1 times the Laplace transform of y of t, so right here, times the Laplace transform of y of t is equals to 3 over s plus 1 squared. Then I can see plus 4s plus 10. I simply could factor out 2 so that we have 2s plus 5, 2 into 2s plus 5, which is still okay. I need to make the transform as a subject of the formula, so that here you could write now the Laplace transform of y of t is equals to 3 over s plus 1 squared plus 4s plus 10. The whole of this we are dividing by, or simply the same as multiplying by 1 over s squared plus 2s plus 1, which you can write as, remember, I want us to take note that s squared plus 2s plus 1 is the same as, remember this a note, NB, so that's the same as s plus 1 squared. So that this can now be written as 3 over s plus 1 raised to 4 plus 4s plus 10 over s plus 1 raised to 2. That's what we have. Now, how do we get the function y of t? That's what you need to ask yourself. So you can write this. If I now operate with L inverse on both sides, so you can just say therefore, to get y of t, I need to operate with L inverse on both sides. So it will be L inverse of 3 over s plus 1 raised to 4 plus 4s plus 10 over s plus 1 raised to 2. And how else can you write this? Remember, let's take note that 4s plus 10 over s plus 1 squared is the same as writing 4 into s plus 1 plus 6 over s plus 1 squared. You can write as that one. I've not changed anything. I've only written the numerator because when you open it, we'll have 4s plus 4 plus 6, which is 4s plus 10. And so this will give you two fractions. This will give you this fraction 4 times s plus 1 over s plus 1 squared, then plus 6 over s plus 1 squared, which when you simplify, you're going to get 4 over s plus 1 plus 6 over s plus 1 squared. So let me bring it back here. So we'll have L inverse of 3 over s plus 1 raised to 4 plus 4 over s plus 1 plus 6 over s plus 1 squared. So now we need to get the inverse from the Laplace transform table, but remember this can as well be written as L inverse of 3 over s plus 1 raised to 4 plus L inverse of 4 over s plus 1 then plus L inverse of 6 over s plus 1 squared. Let me write in another form that is easier to read the inverses. So this could be written as, remember, look at where we started. That the Laplace transform of exponential at times t raised to n will give us this one. This is where we started. We are going to use it because now we are going the reverse way. There is n factorial over s minus a raised to n plus 1. So I want to write this so that it will be easy for us to read the inverses from the Laplace transform table. So this you can as well write as, of course, 4 is the same as 3 plus 1. So I expect a 3 factorial in the numerator over 3 factorial in the denominator. So this is the same as 3 over 3 factorial times L inverse over 3 factorial over s plus 1 raised to 3 plus 1, which is 4. You see, I've introduced 3 factorial in the numerator, so that's why I'm dividing also by 3 factorial. What about the other one? S plus 1, of course, it is just raised to 1, so I'll just factor out 4 outside, then L inverse of 1 over s plus 1. The last term, I can see this power 2, so I expect n plus 1, so n is 1, so I expect a 1 factor in the numerator, so I can factor out 6. L inverse of 1 over s plus 1 squared, and that squared means it is 1 plus 1, so instead of square, let me write here 1 plus 1, so that you can easily read the inverse. So therefore, when you read the inverse, 3 over 3 factorial is the same as, remember 3 factorial is 6. 3 factorial is equals to 6. So what is 3 over 6? That is 1 over 2. So I'll write here 1 over 2. Now here, a is equals to -1 and n is equals to 3. So it will be exponential 1t, just exponential t times t raised to 3. This other one is plus 4. And here a is -1. Of course, we said a is -1, so this should be negative. Remember, this is a is -1 because it's s minus a. So wherever you have s plus 1, that means a is -1. Even here, a is -1, and our n is 0. So we'll have exponential -t times t raised to 0, which is 1, which I don't need to write. Then I can see here plus 6. Here, our a is -1, and our n is 1. So that's exponential -t times t. So you can just say or y of t. So that is our solution of the ODE in part B. Now we can bracket this solution. Bracket it. And so that's our solution for part B. So we have demonstrated how to use the Laplace transform method to solve ordinary differential equations when you are given some initial conditions. Now, what we have found as our solutions are called particular solutions. In this case, we don't have general solution because now we have been given the initial conditions to apply, which we applied to get the particular solution. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving the method of Laplace transform as used in solving ordinary differential equations. Bye-bye.